Welcome back. Earlier, we explored how to calculate the area underneath a curve using a definite integral. And today, I want to look at how to calculate the area between two curves. So what we're going to do is we're going to consider this region S, which is located between the two curves y equals f of x and y equals g of x, and also between the vertical lines x equals a and x equals b. And we're going to assume that f and g are continuous functions, and f of x is greater than or equal to g of x on the interval that we're looking at between a and b. And so to find the area, we can do exactly what we did earlier when we were setting up a definite integral and finding the area underneath a curve a long time ago. We can divide this into strips, n strips of equal width. And then once we've done that, we can use approximating rectangles. And I'm drawing this very crudely, but I think you get the point. Why not finish? We're almost all the way there. I'm using right-handed rectangles, but we know it doesn't matter. And if we cut this into rectangles, we note that the height of each of these rectangles is going to be f of x sub I minus g of x sub I. It's the difference in those functions. And we can pick any sample point in each of those intervals. So I'm going to put stars over our x sub i's. So that's going to be the height of each rectangle. And to find the area of a rectangle, we have to multiply the height times the base, which is going to be delta x, just like we did before. And if we want the sum of the areas of those rectangles, that's going to be sigma, the sum from I equals 1 to n, adding up all of those rectangles. And that gives us a Riemann sum. And we know that if we want to find the actual area, because that's just an approximation, we need to take the limit as the number of rectangles goes to infinity, and that is going to give us our area. However, this is just a definite integral. We know that when we have the limit as n approaches infinity of the sum as I ranges from 1 to n of some function delta x, that is the integral of that function. And in this case, the integrand is going to be the difference of those functions. And so what that means is that our area is going to be the integral from a to b of the difference f of x minus g of x dx. That is how we figure out the area between two curves. And it shouldn't be that much of a surprise, to be honest, because if we extend the vertical lines that give us the ends of our interval, and I'm going to use red to shade in the area underneath that lower curve. We could also, if we wanted to find the area of this region S, we could recognize that this region is the part that's underneath f of x, but not underneath g of x. And so if we took the integral of f of x, we would get the whole area, both the blue and the red. And then to subtract away the red area, we would subtract away the integral of g of x. And we know that that is equivalent to this. This is equivalent to the integral from a to b of f of x dx minus the integral from a to b of g of x dx. And so we can see that we end up with effectively the same thing regardless of how we look at it. So now that we have a method to find this area, let's go through and try out an example. Find the area of the region bounded above by y equals e to the x, bounded below by y equals x, and bounded on the sides by x equals 0 and x equals 1. Well, this is set up to be a very nice area problem. We know that if we want the area between the curves, we need to integrate. And we know that our limits of integration are going to be 0 and 1. That's the interval that we're looking at. And we know that in our integrand, we have to take the difference of the functions. So we have to take the larger function, and we're told that it's bounded above by y equals e to the x. So we're told that that larger function is e to the x, and then minus the smaller function. It's bounded below by y equals x. So that'll be e to the x minus x dx. And all we have to do is evaluate this integral. So we can use the fundamental theorem of calculus. The antiderivative of e to the x is e to the x. And then minus the antiderivative of x is x squared over 2. And we need to evaluate that at 0 and 1. So when we plug in 1, that's going to be e to the first minus 1 squared over 2. And then minus e to the 0 minus 0 squared over 2. So that's going to give us e minus 1/2 in the first parentheses. And then that's going to be minus, and in the second parentheses, all we have is 1. E to the 0 is 1. The other term goes away. And so e minus 1/2 minus 1 is the same as e minus 3/2. And that ends up being the area. Now, this is really the simplest version of an area between curves problem, because we were told which function was on the top and which function was on the bottom, and we were given the endpoints. But there are going to be some examples where we're just asked, find the area between two curves, and you actually have to think about what the graphs might look like so that you can figure out what region is between those curves. So you'll need to figure out which function is the upper function for that region, which function is the lower function, and you'll need to see where they intersect so you'll know what the limits of integration are. So definitely continue watching these videos so you can see some of these problems that are a little bit more challenging.